So we are discussing about the simplest problem of plastic propagation, that is the experiment designed by von Karman and Dewey. So this to get the wave profile, or to determine the wave profile, so we need to apply the boundary conditions. I will write BC for boundary conditions. So boundary conditions is equal to V1T, which is, as we discussed earlier, that the V1 is that velocity of the plate, or when the weight will impact on the wire, impact the plate. So V1, and so we have suppose this wire, this is x equal to 0. So at x equal to 0 we have the V1 velocity, that impact velocity. So u is equal to V1T, the displacement V1T when x equal to 0, at x equal to 0, or it will be equal to 0. So displacement will be equal to 0 at x equal to infinity. So that means up above towards this direction, x is infinity, at a far away from this extremity of the wire. So and at time equal to greater than 0, not it is not at 0, it is at time t equal to greater than 0. So we will get displacement will be 0. So displacement is very less at the top, or it is 0, and it will increase in this direction. So now we will see the different cases, as we know that elastic longitudinal wave velocity and the plastic longitudinal wave velocity are different, and elastic longitudinal wave velocity is higher than plastic longitudinal wave velocity. So as we know that this elastic wave will propagate after the impact, and then this we write it as elastic longitudinal wave velocity. So E L will be elastic longitudinal wave, and then the plastic longitudinal wave will be somewhere here. So this is plastic longitudinal wave. So now the plastic wave, this is the wave front, and this is going in that direction, and we know that this portion. So what will happen in the first case, this region when x equal to 0 to x equal to C1t, or we will write this way. So x equal to 0 to x equal to C1t. So the wave velocities are for plastic longitudinal wave velocities, it is C1, C subscript 1, and for elastic longitudinal wave velocity this is C subscript not, actually C naught. So coming to this again, so in the region 0 to C1t, so this region, so our the strain will be constant, constant, and that is we are denoted as epsilon subscript 1, that is equal to 1 epsilon 1. And similarly in the region number 2, so let us say this region, so this is x is greater than C1 t, smaller than C0 t. So in this region x by t will be equal to d sigma, d epsilon and rho naught. This will be we'll have an expression like this, and then the other region higher than x, higher than C naught t, so x greater than C naught t, the strain will be equal to 0 because the elastic wave does not reach at this portion. So that is why the strain will be equal to 0, and the plastic wave, as you can see, the plastic wave is following the elastic wave, and that is why these three regions like region number 1, 2 and 3. So there are three different regions, so we can see it from here, and also we know this x is increasing in this direction. So here we can see that the material flow, that particle velocity towards the downward direction, and but wave is in the upward direction. This is because this is a tensile wave. So we will now see the discuss about the wave profile. So we will see the distribution, how the strain varies with a function of x by t. So how strain will vary with function of x by t. So that we know that for a plastic wave, the strain will be constant epsilon 1, and then so it will take a shape like this, and then finally this is C naught elastic longitudinal wave velocity, this is plastic longitudinal wave velocity. So this is actually plastic wave front, and this is elastic wave front. So as we discuss, this is the number 1 region where 0 x c is x takes the value from 0 to C1 t, and this region where x is greater than C1 t and smaller than C0 t, where we discuss that x by t will look like this. We'll take the expression d sigma by d epsilon divided by rho naught and square root of the whole thing, and then here x greater than C0 t will be your strain will be equal to 0. So this is at any time, it is at any time t, and for different times after the impact we can get different wave profiles. So suppose at time equal to t1 and time t2, so we will draw this. So this will look like this is at epsilon 1, so this profile will look like this. This is your C1 and this is your elastic wave velocity C0. So, this is the distance as you can see from the previous slide. So, x in this direction, and here at time t2, this is at time t1. So, at time t2, so it will look like this. So, we will extend this part little above. So, this is C0, this is C1. So, as we can see that that at time t2 this has this same maximum strain, but we can see that this portion of the curve is like spreading out. So, you can see the difference of the wave profile in for time t equal to t1 and then time t equal to t2, where your t2 is greater than t1. So, here just important to mention that this is what we plotted here is x by t. It can be for any time t, and then here we are keeping only x and the y axis in both the cases, and there are two times t1 and t2 where t2 is higher than t1. So, now we want to find the maximum stress and strain. Strain means as a plastic strain undergone by the wire So, this is the maximum stress and this is maximum plastic strain. So, we want to find the maximum stress and maximum plastic strain undergone by the wire for a particular impact velocity v1, and we will now derive the expression of the strain in terms of the impact velocity v1, v subscript 1, and we will again find the maximum permissible impact velocity, and that means which the impact velocity, which value of the impact velocity can produce the necking in the wire. So, that means necking instability in the wire. So, that is the maximum permissible impact velocity that we will get the derivation of that very soon. But before that, what we want to do is we want to get the strain in terms of the impact velocity. So, to find this at a specific impact velocity, v1, so that we know that earlier we showed this v1 when the weight impacted the plate. This is the v1. So, what we will do is we will try to get the displacement of the bottom part of the wire. So, bottom part of the wire, the displacement in terms of displacement as a function of time, that means in terms of impact velocity. So, displacement at x equal to 0, that is the bottom part of the wire, will be equal to v subscript 1, that is the impact velocity multiplied by time. So, why we are doing this? Because we want to get the expression of maximum stress or the maximum strain. So, for that we are starting from displacement. So displacement, we know that the bottom part of the wire's displacement, we can find it out. We can find it out from the impact velocity. So we need to consider here the force increase. Suppose we have the wire, we take a small element here. So we know that there will be a force increase, that means the force increase, which we will write as dA sigma naught. We will call it as the force increase, because as the plastic wave or the elastic wave is moving upward, that means this is, let us say, the wave direction. So what will happen is the force will increase from the bottom part to the top part, and we are taking a small element dx here, and we assume that this force increase travels the distance dx in time dt. So we know that the plastic wave velocity for a particular stress level sigma naught. So let us say we will write here the plastic wave velocity for a particular stress level sigma naught, it can be written as dx by dt. So at time dt, I mean that wave cross that this dx distance, and during that the force increase, that is, or we can write df force increase equal to dA sigma naught, that is area multiplied by the sigma naught. Area is the cross sectional area. So this will be equal to dx by dt. Now V phi naught is equal to dx by dt. So what we eventually will do is, so here we will write displacement. So what we eventually will do is, we will apply the conservation of momentum for this small element. So this, we can relate this force increase, which is traveling upward. So force increase A sigma naught is traveling upward, and we discussed that it crosses the distance dx in time dt. So that will be equal to, if we apply the conservation of momentum, so then it will be equal to m dv dA sigma naught dt. So this is, m is the mass of that element, and dv is the differential of the velocity, and so which will be equal to the force increase into the time required to cover that distance dx. So as we know that this velocity and dv we have in the downward direction. So now the mass of this segment, if we consider the rho naught as the density, and we know the cross sectional area is A. So the mass will be written as dx rho naught A into d small v, we can write this is small v, it looks like capital V here. So, we can write it as small v, which will be equal to d A sigma naught dt. So, we actually can keep out this A outside, A is a constant for that plastically deformed portion. So, we can write it this way, this sigma naught. So, then we can cancel out the area term and also then sorry. So, what we can find from the above that relation of plastic wave V p naught. So, we can find that dt equal to dx by V p naught. So, where in this we can use that, or rather we will use it here itself. So, this is dx V p naught. Okay. So, now what we can do is dv, we can cancel out dx and a, and that will give us 1 by rho naught d sigma naught divided by the plastic wave velocity at a stress level, the sigma naught. So, now our aim is to find this relation between the impact velocity and stress or strain. So, then we will find the maximum permissible impact velocity, that means which corresponds relates to the necking of the wire. So, our aim is to find the relation between V1 and stress sigma or epsilon. So, where we will write, let us say V1 and epsilon 1, we will get the relation for this, for impact velocity with the strain. So, now from the earlier expression, so the earlier expression was this expression, the differential of the velocity, that is d v small v 1 by rho naught d sigma naught v p naught. So, if you want to find the velocity at x equal to 0, that is v1. So, v1 is the velocity at x equal to 0. So, now what we need to do is we need to integrate the above equation. Why we are integrating? Because the velocity is 0 at the top and the maximum at the bottom. So, if we integrate this differential of v, what we can get is the v1 is small v, and that will be with a limit of 0 to sigma 1. So, this will be d sigma naught divided by v p naught, which will be again 0 to sigma naught. We know that the plastic wave velocity v p naught can be written as the square root of d sigma naught d epsilon divided by rho naught, the mass density. So, then what we can write is here is from this earlier expression, oh sorry, we have an earlier expression, we have a rho naught here. So, this is rho naught d sigma naught d epsilon divided by rho naught, and this is d sigma naught. So, if we simplify it, simplifying V1 is equal to integration from 0 to sigma 1 d epsilon divided by rho naught d sigma naught. So, this can be, we can further what we can do is we can change the limit, changing the limit to epsilon strain, that is from 0 to sigma 1 to 0 to epsilon 1, because we want to find the relationship of V1 with respect to epsilon 1. We so we want to change the limit to strain instead of the stress. So, what we can find is okay, we will do the calculations here itself. So, this is basically 0 to sigma 1 which will be like d epsilon and d sigma naught divided by rho. So, what we can do is we can get here d epsilon square, and outside we can get one more d epsilon, so that in here we can write it in terms of 0 to epsilon 1 d sigma naught d epsilon rho naught whole thing, the square root of the whole thing d epsilon. So, this is now we have changed the limit. So, this is the relation we got for V1 with a limit 0 to epsilon 1. Sorry, I left it square root over rho naught, and please note that, and also this rho should have been rho naught. So, to get a general solution, we need to get a we need to have the stress strain relationship here, because general solution is not possible of the above equation unless we assume a relationship between stress and strain. So, we know that power law constitutive relation, the common power law constitutive relation we will be using, that is all of us know that this k epsilon to the power n. So, sigma equal to k epsilon to the power n, where earlier we have discussed about this. So, this k and n are two material constant. So, this is the relation between the sigma and epsilon in the plastic region of the stress strain curve that we have already discussed in a previous lecture. So, basically what we want to do it from here is for a known V1, for known V1 and a constitutive relation which we have just we have written here. So what we can do is we can determine the strain. So we can determine the strain epsilon 1. So that is epsilon 1 is the maximum plastic strain that undergone by the wire. So that expression we will find it in terms of the V1, that is the impact velocity. Now let us see how to get that, because we have this constitutive relation which is sigma equal to k epsilon to the power n. Now we have the earlier relation which we got this one. So we will try to use our constitutive relation in this expression and to find out the impact velocity. So from here d sigma by d epsilon, by we are doing this because we need to know that d sigma by d epsilon expression. So this is will look like this, and then from the expression in the previous page, so what we can do is V1, okay, I will write the expression what we have found in the previous page. So we found in the previous page that that impact velocity expression is 0 to epsilon 1, write it like this, d sigma naught d epsilon divided by rho naught whole thing square root d epsilon. So now from this what we can do is we can use this expression in these you can use that for the expression of V1. So what we will get is the k n and rho naught will come out of this integral. So this will be square root of this, and then integration 0 to epsilon 1 epsilon to the power n minus 1 divided by 2 d epsilon. So here we know that this expression will be k n rho naught, this will be epsilon to the power n minus 1 divided by 2 plus 1. So better we will make it look more clear. So divided by n minus 1 divided by 2 plus 1. So we have a limit from 0 to epsilon 1. So directly what you can do is you can write this as epsilon 1, because the 0 will give a 0 value here. So now we can write V1 k n rho naught n plus 1 divided by 2, and then epsilon 1 to the power n plus 1 divided by 2. Okay. So ultimately we will express epsilon 1 in terms of V1. So the opposite one, why we are writing V1 square, because we had a 2 here, this 2, so that will go this side. So this will be V1 square n plus 1 whole square for k n, the entire thing to the power 1 by n plus 1. So this is the expression So, this is the expression for maximum strain, or we will write maximum plastic strain undergone by the wire. So, this is the expression. Sorry, I have left the square root over Kn divided by rho naught. We want to find the maximum permissible impact velocity that is related to the necking of the wire. That means, if we exceed that velocity, the necking instability will happen to the wire. So, we do not want necking in the wire because that will eventually fail the material. So, that is why we want to calculate now what is the maximum permissible velocity that will not allow any necking in the wire. So, maximum permissible impact velocity So, instead of V1 what we will write? We will write V maximum. So, this is nothing but the V1, we will write V maximum here. So, there is permissible the word, this means that corresponds to necking instability. I hope all of you know about necking. So, suppose in a tensile test with a universal testing machine of a ductile material, when you are doing this tensile test, the ductile material will form a neck in this region. So, neck formation. So, this is called necking, and in the engineering stress strain curve, you know, for a ductile material. So, the ultimate tensile strength point will be the point for the necking. So, we want to calculate the V max. For that, so we need to find a stress or strain at which the specimen will start to neck. Stress at which necking will start can be found out with something called considered criterion. Considered criterion is used to get the stress at which the necking will start. So, as we know that the necking starts at the maximum load. So, now as we know, the load P can be written as sigma A, sigma multiplied by the cross sectional area. So, if we write differential of the load, which we can write as A d sigma plus sigma dA, and dP will be equal to 0 because that happens in the maximum load, the necking. So, again from volume preservation, we know that minus dA by A, the cross sectional area, equal to dL by L is equal to epsilon, the strain. This sigma, actually d epsilon will give us the d epsilon. So, from this relation, so what we can get is dA by A equal to minus d sigma by sigma will be equal to minus d epsilon from this relation about the volume preservation. So, now from this we can have a relation d sigma by d epsilon is equal to sigma. So, if we have it, this is what we have drawn is engineering stress strain curve. Engineering stress strain curve, and let us say if we draw a true stress strain curve, true sigma. So, the true stress strain curve, let us say, will look like this, and so this is the variation of sigma, and then the d sigma by d epsilon, which is also known as the work hardening. So, this will look something like this. This is d epsilon, d sigma by d epsilon, and this point where d sigma by d epsilon is equal to sigma, this point that corresponds to the ultimate strain, that is actually the strain at necking. So, this is, so now we got this relation d sigma by d epsilon is equal to sigma at the point of necking. Finally, to get our maximum impact velocity, the maximum we can call permissible impact velocity, we want to do something more. So, what we will do is d sigma by d epsilon is equal to sigma and we know that the sigma, the constitutive relation is sigma equal to k epsilon to the power n. So, here if we use this k n epsilon to the power minus n, and then here k epsilon to the power n, which will give us, k will be cancelled out, which will give us n equal to epsilon. So, basically that this epsilon is the maximum strain at that is related to necking, or otherwise we can write is epsilon maximum is equal to n, the maximum which is related to necking. And from our earlier expression, okay, before going to that, I just wanted to tell you this for engineering stress strain. So, d sigma by d epsilon will be different, this will be 0 for at the ultimate tensile stress point, ultimate tensile strength, this will be equal to 0. So, what we had in the earlier expression is we had the maximum plastic strain in terms of V1, that is impact velocity. We will use this the expression, however, we need the other way around. So, we need the maximum permissible V1, that is the impact velocity in terms of epsilon 1. So, and then we know that the epsilon can be replaced by n, that work hardening exponent. So, then the final V1 we can write it as k to the power half n to the power n plus 2 by 2 rho naught half to the power half, and then n plus 1 by 2. So, this is the expression for V1. So, this is the maximum impact velocity, that means that lead to necking instability, or you can see that this expression is without any stress and strain term, like without any sigma or epsilon term. So, we have only these constants k, n and mass density rho naught. So, what we have discussed in this lecture is plastic wave of uniaxial stress. So, we discussed about the simplest experiment designed by von Karman and Dewey. So, we have derived the expression for the maximum plastic strain experienced by the wire in terms of the impact velocity V1, and also we discussed the maximum impact velocity that can produce necking, and this is all for today's lecture. So, we will discuss about combined plastic shear wave and longitudinal wave in the next lecture, and also we will discuss about the Taylor's experiment. Thank you.